This video is all about suffix notation, specifically Einstein summation convention. If you've done your undergrad degree in the undergrad maths tripos here, this is something you should be relatively familiar with. But if you're coming to fluid mechanics from a more engineering focused background, this might be entirely new to you. Now these concepts make dealing with vectors and matrices and more generally tensors a lot more straightforward, and they'll be used all over the Part 3 fluid mechanics courses. So it's really important that you start the year confident in manipulating expressions of this form. And so to start with, I'm just going to introduce some notation. Now, in this course and in many of the courses this year, we'll be using the standard notation you've seen before of denoting scalars just with letters. No adornment, so things like F, G, and H will denote scalars. Vectors will be denoted with underlines, U, V, and W, say, as examples. And matrices will double underline. So we've got A, so for example, B, C. And in general, the rank of the tensor is number of underlines. So scalars are 0 rank tensors, vectors are 1 rank tensors, and matrices are 2nd rank tensors. So just the number of underlines denotes the rank of the tensor. And quite often we want to deal with the components of tensors, especially obviously components of tensors of higher rank. So for example, if I have this matrix U, which is equal to U1, U2, U3, etc., or this is vector, sorry, the ith component will denote Ui. So U2 is the 2nd component, for example. If we have a matrix, say A is just a 2 by 2 matrix, A11, A12, A21, A22, then Aij is the ijth component. This is all hopefully very familiar. But these sort of component notations are really handy when you want to actually do things. So for example, if I have a vector A and I want to dot it with a vector B, we can write this, say we're working in 3 dimensions, as the sum Aj, Bj over all of the elements here. Alternatively, we can take the product of a matrix with a vector. So we could have A times B like this, and this would, let's look for the ith component of this, and we know from our rules of matrix multiplication that this is just going to be A, I, J, B, J. So again, summing over the components. This is perhaps a little misleading because A above is a 2-dimensional matrix, so I'm just going to rewrite that 3 as a 2. But anyway, and maybe just to save confusion, we'll make it all 2D. But this gets very handy, but it also gets very messy. So a good example would be, let's calculate the trace of A, and this is just going to be the sum of AII, i.e. the sum of all of the diagonal elements of the matrix. That's all fine, but say we wanted to calculate the trace of something a little bit more complicated. So we wanted to calculate the trace of A, B, A transposed, where these are all 2 by 2 matrices. Well, if I wanted to do that, I have to have 3 sums. I have to have a sum from I equals 1 to 2, a sum from j equals 1 to 2, a sum from k equals 1 to 2 of A, I, J, B, J, K, A, I, K. And this gets really messy when you're handling lengthy expressions with lots of these sort of things. So can we get rid of the summations? It turns out that's exactly what Einstein summation convention does. So we need to, we basically implicitly assume a summation whenever there's a repeated index. So for example, if I wanted to take A dot B, I would now write this as AI, BI with the summation implicit. So you should read this equals the sum of I up to n, where the number of dimensions is implicit as well from context, of AI, BI. And whenever you see a repeated index, that means you sum over that index. So this is the key to Einstein's summation convention. Whenever there is a repeated index, these indices are called dummy indices because you could call them what you like. I mean, this could be AK, BK, and that would be exactly the same thing because you're summing over all of the Ks. So these are called dummy indices. And a dummy index can only appear it can only appear twice in the expression. If it appears more than twice, you've gone wrong. But there's another type of index. So say I wanted to take the ith component of A times B, where A is our matrix from last time. The ith component of this, well, we know from our rules of vector matrix multiplication that this is Aij Bj, where the sum is happening over the j's. So this is the same thing as the sum to n over j of Aij Bj. And this index here is called a free index. And the free indices on each side of the equation have to match. So free indices Okay, so this is really quite handy. Obviously there's a lot that's implicit in this notation. The number of dimensions is implicit, but so long as you follow the rules of matching free indices on both sides and never having more than one dummy index, things become a lot quicker to write. So for example, our trace of A is just going to be AII, and our really complicated trace expression from last time, trace AB A transposed, which was a real mess to write last time, is just written AIJ BJK AIK. Now, if this looks a little bit of a mess, well, I'll show you some examples in a bit of how it makes calculation really, really easy. But first, I'm going to introduce two quite important tensors that come up quite often in these sort of problems. And the first one of them is called the Kronecker delta. Now, the Kronecker delta is basically equal to the identity matrix, i.e. delta ij is 1 if I equals j, i.e. the diagonal components down this matrix, or it's equal to 0 if I does not equal j. And so we've got lots of properties and ways that we can contract this with vectors and other matrices. So for example, if we've got a vector A, we take AI delta ij. Remember from the last slide, this basically means the sum over I AI delta ij. Well, this is just going to be equal to aj, because the only non-zero term here is delta ij when I equals j. And doing this is called contracting over the index I. We can do lots of other things. We can take delta ij delta jp, for example, and this is only non-zero when j equals p, so this is equal to delta ip. If we take delta ii, remember what this means? This means sum over I of delta ii, and so this is equal to n in n dimensions, i.e. it's just the trace of the identity matrix. And you can construct more complicated things. So you've got the vector A and you've got the vector B, and you take AP delta B PQ BQ. Well, this is equal to AP BP, because this is only non-zero when P equals Q. Remember from the last slide, this is equal to A dot B. Let's just see what this is equal to. This is equal to A dot the identity dot B. So yes, of course, they're the same. A slightly more complicated tensor, again, works in 3 dimensions. This one is the so-called Levi-Civita or alternating symbol. Now recall that we're in R to the 3 here. So I, j, and k take values 1, 2, 3. Now epsilon ijk is plus 1 if ijk is an even permutation of 1, 2, 3. It's minus 1 it's an odd permutation of 1, 2, 3, and it's 0 otherwise, i.e. if we have repeated values. So an even permutation is one you can get to through an even number of swaps. So 1, 2, 3 is an even permutation of 1, 2, 3 because there are 0 swaps. Another example might be, let's swap 2 and 1 and then swap 2 and 3. So we end up with 3, 2, 1. That's the same. But something like 1, 3, 2 is an odd permutation. Just double checking 3, 2, 1. Let's just get rid of that for now because I can't on the fly check the number of swaps going on there. Generally, if you have a cyclic permutation, it's going to be even. So this is quite handy because this actually pops up in a lot of things like the cross product or the curl, for example. So because of even permutations, we have epsilon ijk equals epsilon jki equals epsilon kij because of the cyclic property. And we have lots of other things like if that A cross B, the ith component of A cross B, is equal to epsilon ijk aj bk. So you can check this by doing the summation yourself. We're contracting over the j index and the k index here, and you should find that that exactly comes up with the definition of the cross product that you've have seen before. So there's a few identities and tricks that we can use with these special tensors. A key example is, let's consider if aij is equal to aji, i.e. if A is a symmetric matrix, then if we contract it with the alternating symbol, like so, we know that this is going to be equal to epsilon I j k a k j, because this akj is the same as ajk. But because these are dummy indices, we can label them whatever we like because they're just being summed over. So let's just swap the definitions of k and j and get this equals epsilon I k j a j k. But epsilon ikj is equal to minus epsilon ijk because it's an odd permutation. So this is equal to minus epsilon ijk ajk. We've got epsilon ijk ajk is equal to minus epsilon ijk ajk. So it's equal to 0. And this is because epsilon is totally antisymmetric. And that means that if you contract it with something symmetric, you get 0. There's another very handy identity that you can prove by considering components that we will use a few times and that is worth committing to memory, and that's epsilon ijk, epsilon ipq. So contracting over the first index is just equal to delta jp delta kq, minus delta jq delta kp, with this being the Kronecker delta. You can check this yourself by considering each element. It's a little bit of a faff, but you get there in the end. Right, should we actually solve some proper problems with these? So if I've lost you at any point here, hopefully things become a little bit clearer when we apply it to some real life situations. So the first thing we're going to do is going to prove the vector triple product identity. You might have seen this before in a linear algebra course, but let's start by considering the ith component of this. And recall that A cross B I is equal to epsilon ijk ajbk. So the ith component of this is going to be epsilon ijk aj b cross c k. And then we apply the same identity again to get epsilon ijk aj epsilon kpq bp cq. Okay, let's bring these alternating symbols together, and we get epsilon ijk, epsilon kpq, aj, bp, cq. Now, it turns out that epsilon ijk is exactly the same thing by a cyclic permutation as epsilon kij, because that if this is an even permutation, if ijk is an even permutation, so is kij. If it's an odd permutation, so is kij. So we can write this now as epsilon kij, epsilon kpq, aj, bp, cq. Okay, this is in the form of the identity we had last time. So recall that epsilon kij, epsilon kpq is equal to delta ip, delta jq, minus delta iq, delta jp. So this whole expression is equal to delta ip, delta jq, minus delta iq, delta jp, aj, bp, cq. So this first term, all of the p's we replace with i's, all of the q's we replace with j's. So we have aj, bi, cj, minus all of the q's we replace with i's, all of the p's we replace with j's, aj, b, p is being replaced by j, c, I. So this is equal to a dot c bi minus a dot b ci. Okay, our free index is the same on both sides. We're taking the ith component and our free index is I, so we can then just get the result we wanted. Perfect. The two sides match up. So you can see here that index notation is a really handy way to prove vector identities that actually are otherwise quite nasty to prove. Let's do one further example. This is an example from fluid mechanics. You don't have to understand the fluid mechanics in it to be able to do it. But Stokes' equations, which are covered in another one of these videos, can be solved for a point force at the origin to get this solution here. U is related to the point force using this second rank tensor here. G is very suggestive here. This is a Green's function. You've seen these before. If you have a force dipole, so you have two forces pointing in opposite directions separated by this little vector d, and you take the limit as d goes to 0, so you have these two forces at the origin, we actually notice that the velocity field is given by this expression involving the gradient of g. Now it's really difficult to work out what the gradient of a tensor is in general, but with index notation it's not at all. So we want to find the ijk element of grad g. So remember that g is second rank. So grad g is third rank. So it's going to have 3 indices. In the same way that grad of a scalar is a vector, you're upping the rank by 1 every time you take the gradient. So we need two little results really to proceed any further. If we want to differentiate xj with respect to xi, this is 1 if I equals j, i.e. dx by dx is equal to 1, but it's 0 if I does not equal j, i.e. partial y by partial x is equal to 0. Let's maybe just write these down just so it's clear what we're doing. So this has to equal delta ij. And then let's look at what dr by dxi is, where r we know is the square root of the modulus, is the modulus of the vector. So we can write it like this, or remember this is equal to x dot x. That's why I've written the square root of a square, because this is d by dxi of the square root of xj. Okay, let's use the chain rule here. It's going to be d by dxi of xj times 1/2 times 1 over. Let's just relabel the dummy indices here so we don't end up with more than 2 hanging around. And then further doing the product rule here, we end up with xj delta ij over root xk which is just going to be equal to xi over r. Lovely. Okay, so these are two handy results that we'll use to find the gradient of g. So let's get a new screen. I should have summarised the results here. So we want to find grad g ijk, which is going to be d by dxi of gjk, which is going to be d by dxi of delta jk over r plus xkx, or xjxk, sorry, same thing, over r cubed. Okay, we can use the chain rule here quite handily, and we get dr by dxi times minus 1 over r squared times delta jk. Again, we get minus 3 over r to the 4 dr by dxi times xj xk, and we also get delta ij xk over r cubed plus delta ik times xj over r cubed. Now we know what dr by dxi is, so we have minus 1 over r squared xi delta jk over r, and we have minus 3 on r to the 4 times dr by dxi again, which is just going to be xi over r xj xk, plus this is going to be delta ij xk over r cubed. This is going to be delta ik xj over r cubed. So let's just tidy this up a little bit, and we end up with an expression that works out to be, let me just double check that nothing silly has gone wrong here, minus 3 on r to the 4 xi xj xk plus delta ij xk on r cubed plus delta ik xj on r cubed minus delta jk xi on r cubed. Turns out there's a slight mistake here, that we have r to the 4 times r, so this should actually be r to the 5, but this is our result. It's very messy, but it would have been very difficult to do this without Einstein's summation convention. If this is still posing problems for you, there's a bit of recommended reading here, the Part 1a Vectors and Matrices course, some notes for this that are produced online, but if you've got any questions, bring them along to the in-person session,